Welcome back, viewers, to my physics channel. We've been moving together. This is Dr. DORCAS NGIGI. Today we are going to look at image formation by diverging lenses. Okay, this is a biconcave lens. In the last lesson, we looked at image formation by converging lenses, which we call biconvex. So I hope we still remember that. So today we are going to look at what about a diverging lens. Now, the good thing with a diverging lens is the type of image is just the same, okay? Unlike in the converging lens, where we had some images that were virtue, others were true, some were magnified, others were diminished, some were others were same size as the object. In a diverging lens, all images have the same characteristics. They are virtue, and they are, of course, if they are virtue, they are upright. They are smaller than the object, okay? And they all fall between the principal focus and the optical center. So that is very important. So let's look at image formation. So image formation by diverging, which is also called by concave lenses. Okay. Now we're going to draw the stem. Now by now we've gotten used to drawing these things. So we are using a biconcave, don't forget. Then we have to draw the vertical line and then indicate the shape, the type of lens we are using. The other, we need to draw the principal axis, measure the distance from the optical center to F, make sure it is equal to the distance from the principal focus to 2F, center of curvature. Same to the other side, don't forget. We say the distance from the optical center, that is the center of our lens, to F, which we call the focal length, and the distance from the principal focus to the center of curvature to F, the two distances are equal. Or better yet, 2F distance is twice the F distance. Okay, now with that, let's put an object anywhere. Let's put the object between 2F and F. Okay, then follow the rules. What are the rules here? Rule number 1, the ray that is parallel to the principal axis, how will it be refracted? It will be refracted so that it looks like it is coming from the principal focus. So it will be refracted like that. Remember, we are using a diverging lens. So the ray that was parallel to the principal axis will be diverged. It will be refracted as a diverging ray, and it will be diverged as if it is coming from the principal focus. Don't forget. Okay. The other ray we can have is the one that is very obvious. A ray that is coming from the tip of the object through the optical center. That ray, we said, passes undeviated. Remember, we said any object you choose, a point on that object is a source of many rays. Okay? Any point on an object is a source of light. And meaning a source of light, just like we would have a bulb, there are so many rays coming from a single point. So some of these are the rays we are using. We only need 3 of them, or even 2. One that is parallel to the principal axis, and one that is passing through the optical center. The rest are not very necessary. Those 2, if we use them, then we get our image. Okay, so the other one is a ray coming from the object, passing through the optical center. That one passes undeviated. Okay, now These two are enough because we get a point where the two rays intersect. This is a ray, this is also a ray, a virtue ray, because a true ray is going away from the lens. So anything behind that is produced behind that ray, that true ray is imaginary. Anything produced behind the true refracted ray, that one is imaginary. So where this imaginary ray and that true ray coming from the tip passing through or meet, that is where we form the image. Now, why is the image virtue? Why is the image, why have I put a dotted line? Because our image is virtue, courtesy of intersection of one of the rays being virtue. Okay, that image is like that. So how would I say is the image characteristic? Image characteristics. So 1, it is upright. As you can see, the image is upright. 2, of course, it is virtue. Being upright, just like the object, simply means it is virtue. It cannot form on a screen. Anytime an image has been formed by one or several rays that are virtue, that image cannot form on a screen because there is no ray that the rays have not met. They are imaginary. The true rays are the ones that are going away. Anything behind is not a ray, is an imaginary ray. It is just looking like it was coming from there. So it's an imaginary ray. It is not there. It does not exist. So such images are virtue. They cannot form on a screen because the rays do not interact really. Okay, number 3, what can you say about the size? If you look at the size of the image and the size of the object, of course, it is diminished or simply smaller than the object. It is smaller than the object. And number 4, where does it form? It forms between F and O. So formed between F and O. Okay, that's very important. Now we can choose, just for clarity, let's choose another point. Okay, let's choose maybe an image behind 2F. So where will it form? Okay, so it's too big. So following the rules, now we can do it faster. You've gotten used to it. So that will be refracted through the principal focus. Okay, and the one that, sorry for that, we're using a diverging lens, so it will be refracted as if it is coming from F. And the other one, of course, will be coming from the from the tip of the object through the optical center, and that should pass undeviated. So where do they meet? Of course, they meet somewhere there. Okay, so that's our object and that's our image. Now, if you look at the two images, the characteristics are just the same. It is upright, it is virtue, it is diminished, meaning it is smaller than the object, and it is formed between F and the optical center. Is the optical center. And something else maybe we should add is that it is formed same side as the object. Okay, it is virtual, it is upright, it is smaller than the object, meaning it's diminished. It is formed between the principal focus and the optical center. And finally, it is formed the same side as the object. Now, what I want to bring out here is, when we are using a diverging lens, that is biconcave lens, irrespective of where we put our object, whether it is behind C or at C, between C and F, at F, or between F and O, regardless of the position of the object, the image characteristics will be the same. The image will be upright, it will be virtual, it will be smaller than the object, it will form between F and O, and it will form the same side as the object. So all images formed by diverging lenses are the same regardless of the object position. So that is very important. All images by diverging lenses are the same. They have the same characteristics irrespective of the object position. So the other thing I would like us to look at today is something we call magnification. So magnification So let's use a concave mirror, a converging lens, not concave mirror, you're not using mirrors. So let's say we are using a converging lens. Then we have F, we have 2F, we have F, and we have 2F. Let's say we put the object between F and 2F. Now, following the rules, remember we are using a converging lens, so that ray should be reflected through the principal focus. And then we have another ray coming from the tip of the object to pass through the optical center, and that one should pass undeviated. Where the two rays meet, we said we draw a straight line to touch the principal axis. Okay, like that. So this is our object, and that is our image. Okay. Now, to understand magnification, there are terms that we need to understand. The distance from the optical center to where we have the object, we give it symbol U. U is called the object distance. Okay? The distance from the optical center to where we have the object, we give it symbol U, and that is the object distance. The distance from the optical center to where you found your image, remember there is a screen there, that distance is given the symbol V, and V simply means image distance. So what is magnification? Magnification is a measure of the size of the image relative to the size of the object. So it is image height divided by object height is also equal to image distance divided by object distance, which is equals to image distance, which we said is V, divided by object distance, which we said is U. So remember, why are we saying this? Because we said as the image moves far away from the lens, it becomes bigger, and the distance also becomes larger. So the larger the image distance, the larger the image size. So when the object is at infinity, as we bring it closer to the object, to the lens, the image moves away from the lens and the size of the image increases. As the image comes closer to the lens, it becomes smaller as its image distance also becomes smaller. So image height and image distance are proportional. Image height and image distance are proportional. The same way that object height and object distance are also proportional. So magnification can be given as image height divided by object height, or image distance V divided by object distance U. So it is simply a measure of the size of the image relative to the size of the object. So we give it symbol M is V over U, or image height over object height. Now what would happen if the magnification is 1? Okay, like in the case where the object is at 2f, the image is also formed at 2f and they are the same size. So magnification will be 1 because the object and image are of the same size. If the magnification is greater than 1, then the image is bigger than the object. Then if the magnification is less than 1, then it means the image this time is smaller than the object. And that happens when the object is very far, then the image is very small, diminished. Then the magnification will be less than 1, meaning our image is smaller than our object. Okay, so that brings us to the end of this lesson. I hope you have learned something. So don't forget to like and subscribe, and I hope to see you in my next lesson as we continue with our topic of dim lenses. Thank you very much for watching. Goodbye.